Hi, welcome to the series of CSEC Physics past paper questions. And here I will be just doing one question per video to highlight the type of questions that CXC normally gives on their CSEC Physics exam while helping you to go through these questions as quickly and thoroughly as possible. So stay tuned as I go through various questions that will highlight various topics of the CSEC Physics syllabus. So here we have question 2 from our 2024 June-May exam, and we're going to go through as quickly as possible, highlighting various strategies and hints in which to approach questions like these. So we start with seeing figure 5 shows a bottle filled with water resting on a ground in three different positions, A, B, and C. Now, if we notice, A is upside down normally, B is positioned in the normal position, and C is on the side of the bottle. State the type of equilibrium for each of the following. So in this question, it's more of recalling that there are three types of equilibrium. It can be either neutral, stable, or unstable. Now, if it's neutral, if you think about something being neutral, I mean, it doesn't swift left, doesn't swift right, doesn't go up, doesn't go down. Neutral in itself means whatever you do to the object, it's going to remain in that orientation. So if you look at A, B, C, we see that C is the one that looks more likely than if you roll this forward, you roll it back, it looks the same that it was before, which is on its side. So the only way you can take it from its side is to lift it up and position it differently. So we say that object C is our neutral position or neutral equilibrium. Now if we look at A is on a small area, contact, unlike B that is in a larger contact. And if we remember anything from equilibrium, then the center of mass is always acting vertically downwards. And if we notice, if we tilt A slightly, that vertical line will stop acting on the base of the bottle, which means that if you tilt it slightly, it's more likely to fall to the side that you tilt it to. So therefore, we can say that A is unstable. And B would be our stable equilibrium because it's going to require more force, more tilting for it to actually fall to the side. All right, now let's go to part B that says define the term moment of a force and state its SI unit. And that's 4 marks. So the first thing is we define moments of a force. And we can say that moments of a force is the turning effect caused by a force acting away from a pivot point. And then we can identify that its SI unit is Newton meter because its formula is force times distance. Alright, next part of part C. If figure 6 shows a uniform meter rule balanced horizontal on a fulcrum with a mass, so G being 10 Newton per kilogram. Now, if we notice here that the pivot point is not in the center, right? So the center of the meter rule is somewhere there, and we know the ruler has a weight that always acts vertically downwards like that from the center. So we're going to use that idea later on in this question. So let's tackle the first part that says calculate the weight of the 0.24 kilogram mass. So we know that weight, W, is equal to mass times gravitational acceleration. Now the mass is already in kilograms, 0.24, and they said to use G as 10. So therefore we get 2.4 Newton. And what this means is that this block has a downward weight of 2.4 newtons. Alright, next part, by taking moment, calculate the weight of the meter rule. And that's where this part comes in. Because we know that the 2.4 Newton is going to cause a moment effect in that direction. And the weight will have a moment's direction in that direction. So therefore, we see that the weight will have a clockwise moment and the 2.4 will have an anti-clockwise moment. And according to the principle of moment, it says that the sum of the clockwise moment should be equal to the sum of the anti-clockwise moment. But in this question, we only have one clockwise moment, which would be the weight of the meter rule times the distance that it's away from the pivot. Now here is the trick to find the distance. We know that the full thing is 1 meter. And we know that from where the mass is to the weight, that is 0.5 meters. And if we know that 0.18 meters is away from the edge of the left side, then we know that this length here would just be 0.5 minus 0.18, which would be 0.32 meters. So therefore we know that this is 0.32 meters, and then it's the weight, the force of the anticlockwise moment, which is 2.4, times its distance from the pivot, which is 0.18. So let's do the right hand side first. So 2.4 times 0.18, and that gives us 0.432. And we have on the right side 0.32 W. So we need W, we divide by 0.32 on both sides, and that gives us W to be 1.35 newtons. And that's the weight of the meter rule. Now, final part of the question, question 2, and for today, is to calculate the magnitude of the force of the fulcrum acting on the meter rule. And this is where a principle of equilibrium comes in, which says that all the opposite forces must be equal. So now we know that there are two downward forces, the weight of the meter rule and the 2.4 Newton. So therefore, automatically that means there is an upward force at the pivot point pushing up on the meter rule. So by that logic, then that upward fulcrum force is going to be equal to the 2.4 plus the weight of the meter rule that we just found, which is 1.35. And that gives us 2.4 plus 1.35 gives us 3.75 newtons. And that would be the answer. Now, thank you for watching. Hope you understand a little bit about the concept of moments. And I'll see you next time where we approach another question.